Hello guys, good morning. Good morning to all of you. Am I audible? Am I audible? Okay, so today in this session, we'll be discussing scattering. I think this scattering is left, and other than that, relativistic quantum mechanics is left. Then our quantum mechanics course will be over. Okay, so let us talk about this scattering briefly today. Look, we'll start with scattering and cross section, the relation between these two. So you see, in a scattering experiment, look, in a scattering experiment, one observes the collision between a beam of incident particles and a target material. Okay, so this is what we have in a scattering experiment. We will have a beam of incident particles and a target material. Now, the incident particles will make collision with the atoms of the target material or nuclei of the target material. The total number of collision over the duration of the experiment is proportional to the total number of incident particles. This is important. The more and more number of incident particles you send, the more will be the scattering, and to the number of target particles per unit area in the path of the beam. Look, more the number of target particles on the path, more will be the number of collisions. So this is very straightforward fact. So in these experiments, one counts the collision products that come out of the target. So you send incident particles, it hit a target, okay, the atom in the target. So these incident particles make collision with these atoms, and ultimately we get some output. Okay, so you send too many, you don't get too many, you get little less than that. So after scattering, those particles that do not interact with the target continue their motion undisturbed. Some of them will be undisturbed in the forward direction, but those which interact with the target atom, they can experience or suffer some deviation. Okay, now some of them can also come back in the opposite direction, but those with the those that interact with the target get scattered or deflected at some angle. The number of particles coming out varies from one direction to other. So if you, let's say, place a detector which will count the number of particles scattered, so if you place this detector at different angles, it will count different number of particles. It will count different number of particles. Now on this context, we define the differential scattering cross section. How to define the differential scattering cross section? Number of particles scattered into an element of solid angle d omega. D omega is given by sin theta d theta d phi. So number of particles scattered into a solid angle, let's say d omega, is proportional to a quantity that plays a central role in the physics of scattering. This is called differential scattering cross section or differential cross section. Now differential cross section, as you can see from the name, differential. So here it is d omega of sigma theta phi. So this is scattering cross section, d omega of sigma of theta. This is called differential cross section because you see it is involving the differential. The differential cross section, which is denoted by this, is defined as the number of particles scattered into an element of solid angle d omega in the direction of theta phi per unit time per unit incident flux. Okay, so mathematically it is represented by this formula: d sigma theta phi d omega is equals to number of particles dn theta phi, okay, per unit solid angle d omega, per unit time in incident flux, so that is J incident, number of particles per unit time per unit flux. Okay, J incident is the incident flux or incident current density, current flowing per unit area. It is equal to the number of incident particle per unit area per unit time. So this is J incident. So this differential cross section d sigma by d omega, it will have a dimension of area. Hence it is appropriate to call it a differential cross section. Okay. So this is the basic idea. Now we'll try to understand what kind of how this experiment, scattering experiment, is modeled. So we'll take one model which will explain how the particles is coming, what is happening when they are moving undeviated and when they are getting scattered and all. Okay, so the takeaway from this is d omega is equals to sin theta d theta d phi. D sigma by d omega is equals to this. So this is for a particular solid angle. Okay, differential, you can see this is for a particular solid angle, an element of solid angle d omega. And if you want to get the total cross section, so what we have to do, d sigma by d omega, differential cross section. So if you integrate over the solid angle, it should give you the total, okay, total cross section. Now consider this situation. N theta phi, okay, n represents number of particles, right? Number of particles. Theta and phi will be the spherical polar coordinates, which will help us to denote. Let's say if you have this direction, so this direction will be denoted by theta and phi, okay, in spherical polar coordinate. So just look at this image, try to understand it. Let me just keep it. Look, why we require both the coordinates theta and phi to denote the direction. Let's say if you remember, this is our spherical polar coordinate, right? So let's say if you want to specify this position, what do you do? If you want to specify this direction, what do you do? Look, we join it with the origin. So this angle will be theta. This angle will be theta. And if you draw a projection, then this angle will be phi. So if you want to know the direction, look, R will depend where the point is. It may be here, it may be here. Now if you talk only about the direction, if you are talking only about the direction, let's say this direction. So only theta is not enough. Okay, we need to specify both theta and phi. So any direction will be accurately determined by theta phi. So that is why this theta phi is shown. Okay. Because you can consider it in 3D. With a fixed value of theta, it may be a different position. Okay. So that is why the phi specification of phi is necessary. Now here you see incident particles. So by this simple lines, it is showing that this is a plane wave. Okay, plane wave incident. Now you have a target. Target means some target nucleus, you can say. So target nucleus will have some potential. So when these incident plane waves will come here, it will interact. Okay, it will interact with this potential. So what is seen that most of the particles goes out undeviated, unscattered. You can see the form remains same, only the amplitude, the length is showing the amplitude has been reduced. Okay, so these are unscattered particles and this direction is taken to be z direction, and on the other directions you will have scattering. In other directions you will have scatterings, and in this picture a particular direction has been just shown. A particular direction here has been shown. This direction is for the solid angle d omega. This direction is shown to you. Particles scattered in d omega along the direction of theta phi, and this area will be r square times d omega, because this to this distance is r. So this area will be r square d omega, and d omega sin theta d theta d phi. So this is sin theta and d theta and d phi. This is the scattering between an incident beam of particles and a fixed target. The scattered particles are detected within a solid angle d omega along the direction of theta phi. Okay. So for this case, you see the differential scattering cross section will be d sigma by d omega. Differential scattering cross section will be denoted by d sigma of theta phi by d omega, or d sigma by d omega, and total cross section will be sigma, which is d sigma by d omega times d omega. Okay, then d omega you can put sin theta d theta d phi if d sigma by d omega is expressed in terms of theta and phi. So using this you can solve numericals. So let us take one numerical. This came in June 2015. The differential cross section for a scattering by target is given by this. If n is the flux of incoming particles, the number of particles is scattered per unit time. Number of particles scattered per unit time. Here you can see number of particles scattered per unit time. The number of particles scattered into an element of solid angle d omega per unit time per incident flux. Remember this one: per unit solid angle, per unit time, and incident flux. So per unit time and incident flux, these two is taken care in the J incident. Okay. Do it. Any question? Look, to clarify this n is not the incident one. This n of theta phi is the number of particles scattered in the angle of theta phi, but number of flags will be denoted by, let's say, n, which is going in the forward direction. It is like n maybe incident, then it is hit by target, then it is maybe scattered in different directions, so that may be denoted by n of theta phi. So it is like that, but don't confuse it. So this n incident is included here in j incident. Can you solve this problem? Look, what is given? D sigma by d omega is equals to a square plus b square cos square theta. This is given. So we have to find out the number of particles scattered per unit time. So if I calculate scattering cross section, that will give you number of particles scattered per unit area per unit time. Okay, sigma will be integration d sigma by d omega times d omega. So d sigma by d omega, it is given a square plus b square cos square theta. Okay, now d omega will be sin theta d theta d phi. So we have here two integration, theta and phi, so you can just give double integration to it. So now we can write a square integration 0 to pi d phi integration 0 to pi and 0 to 2 pi sin theta d phi plus b square integration 0 to pi, let's say, cos square theta sin theta d theta 0 to 2 pi d phi. As simple as that. Sin theta d theta is cos theta minus cos theta minus cos theta, so minus minus plus 2, and this 2 pi, so 4 pi a square plus cos square theta sin theta d theta d phi. Cos square theta sin theta, you can write d of cos theta with a minus sign, so this will be cos cube theta by 3, so a minus will come, minus 2/3, and here 2 pi. Okay, so minus 4/3 and minus minus plus, so 4/3 pi b square. Okay, I think this is very straightforward to understand. If I take 4 pi common, so you are left with a square plus b square by 3. So this is the scattering cross section, and hence the number of particles scattered per unit time is for the number of particles scattered per unit time is, if I just multiply with the number of incident particle, then that will give you that number. So 4 pi n times a square plus b square by 3. This is matching with option D. Clear? second integral cos square theta sin theta d theta. So this will give you the value 2/3. This is giving the value 2 pi. You can imagine that let's say u is equals to sin theta. Okay, u is equals to, let's say, cos theta. Du is equals to minus sin theta d theta. Then you can put the limits. Theta was between 0 to pi. So your u will be cos 0 is 1, cos pi is minus 1. Okay. Then you can just simply put the limits, plus 1 to minus 1 cos square theta. So u square sin theta d theta is du with a minus sign. So minus du. Okay. So if you just absorb this minus sign, so this becomes u square du. So u cube by 3 minus 1 to plus 1. So 1/3 minus minus plus. So 2/3. Okay, now look at this. This picture is very important. Here you have shown the scattering. So your incident wave is coming, and you see most of the wave is getting unscattered. So we can say this is the incoming wave and this is the scattered wave overall. So the scattered wave, we can say that it is composed of the unscattered plane waves plus the spherical wave, okay, which is scattered in different direction. So let us write one line: after scattering the total wave consists of a superposition of the incident plane wave. This is the plane wave. Incident plane wave. This is the unscattered plane waves. Incident plane wave and the scattered wave. Okay. So if I write in terms of psi of r, so it is consist of the incident part, okay, it is similar to the incident part unscattered plane wave, phi incident of r plus phi scattered of r. So incident, which is unscattered one, that will be given by the plane wave. So a, let's say A is the constant amplitude, e to the power I k naught dot r. So this is the equation for plane wave we use. So this is the incident plane wave plus the scattered wave will be spherical in nature. So spherical scattered wave is, it will have the scattering amplitude f of theta phi. And now for scattered wave, the spherical wave, we have to do this e to the power I k dot r divided by r. Okay, so this 1 by r factor will come additional. So this is your incident plane wave. Incident plane wave, this is known as the scattering amplitude f of theta phi is known as the scattering amplitude. Okay, and this is spherical wave as overall, the second term. Now the next topic is little bit odd. It may appear to be so absurd to you, but for the sake of completeness, we have to do it. This is where you can see there are a lot of calculations. We are not going into that. We'll be just giving you the minimum necessary things. Okay. So I'm talking about the partial wave method. So just take a note on this. Okay? No, not many question is expected from it. It is important conceptually. On the numerical front, it is not that much important. Okay. The partial wave method. Partial wave method. The name suggests like a complete wave can be thought of combination of some partial waves. So a wave overall is carrying some momentum, right? Angular momentum. So if you consider that it is composed of small waves, so each partial wave, so each small wave will also carry some angular momentum with itself, and if you combine all of them, you get the total angular momentum of the wave. Okay, so this method is applicable. This method is applied when the potential is central. Potential is central. Central potential, you know, when the potential is dependent as a function of r, B is a function of r, like the gravitational, electrostatic potential. All of these are central potential. As you can see, it is talking about this. So here we have some target and we are getting a potential. So if this potential is central in nature, then we apply this partial wave method. Central, that is V of r, it is only dependent on r and is of finite range. That is V of r is equals to 0 if you consider, let's say, r greater than some limit, some finite range r naught, r is greater than r naught. Now this method is in GATE exam, you may get some statement based question. There it may be asked in which case it is applicable. They may create 4 options and you have to select one. This method is useful, really useful, only when the energy of the incident particle, energy of the incident particles is rather low. Okay. Now let us consider a situation that assume a number of incident particles is going or forwarding in the z direction. Assume the incident particle or incident plane wave. It will be better to write incident plane wave. Assume the incident plane wave is moving along the z direction. Okay, so we can express it, the whole wave, as a combination of the partial small waves. We can express it, in terms of superposition of angular momentum eigenstates, each with a definite angular momentum, let's say L, angular momentum L. So we have this incident plane wave, What does it mean? Incident plane wave is denoted by e to the power I k dot r. We have already told you. So this will be e to the power I k r cos theta. Simple as that. So this plane wave is written as the combination or superposition of angular momentum eigenstates small partial with a definite angular momentum L. So it is written as sum over L runs from 0 to infinity. I is the square root of minus 1, I to the power L times 12 plus 1 JL of KR PL of cos theta. So just for the sake of completeness, you note it down. What is I you know, square root of minus 1, L you know, JL of KR. What is this JL of KR? And PL of cos theta you know, legendary polynomial. So you see, this is how you can express it. Now you can imagine it in this way, that the complete wave is there. So it is decomposed into different parts, and each part has its own angular momentum L. Now when you go from one partial wave to other, there is a phase change. There is a phase change of pi by 2. Okay. So when we do it, let's say do it L times, it becomes L pi by 2, each time pi by 2. So L times L pi by 2. Now this JL of KR, this has a value, JL of KR, let's say in the limit KR tends to infinity, it is given by sine KR minus L pi by 2 divided by KR. So in the limit of r tends to infinity, how we write the incident wave? In the limit of r tends to infinity. So you see, L is equals to 0 to infinity, I to the power L 12 plus 1 PL of cos theta, PL of cos theta. Next we have to write this JL of KR, or r tends to infinity, sine KR minus L pi by 2 by KR. So sine is what? Sine we can write e to the power I KR minus L pi by 2 minus e to the power minus I KR minus L pi by 2 divided by 2i, right? So we have written this, and this kr was there, so we can write kr here. So this is your incident wave, effective incident wave. And this can be written as 1 upon 2I kr. This is a constant term coming out of the summation. L is equals to 0 to infinity. Okay, 12 plus 1. Now we are writing it in this way. E to the power I L pi by 2. Okay, so we can write, and e to the power I to the power L is there. So it can be done something. E to the power I pi by 2 into L and I to the power L. This can be combined, and this I to the power L, and here e to the power plus I into L pi by 2. So we can write it minus 1 to the power L plus 1 e to the power minus I k r plus e to the power I k r times PL of cos theta. So this will take this form after a little bit of calculation. Now after getting scattered from the potential, you try to understand this. After getting scattered from the potential, it will become psi out. Psi incident of R will become psi out of R. And here what is happening? Here we have considered a potential which is central in nature and of finite range. So the job of this kind of potential is to introduce a phase change of, let's say, delta L. Okay, a phase change of delta L will be there. So the scattered wave, because you see many factors are there. Energy of the incident particle is low. Okay, so psi scattered will take this form, psi out of R at R tends to infinity. This will take the form 1 by twice I k r. Look, it will be very similar to incident wave, only the phase shift will be there. 12 plus 1 minus 1 to the power L plus 1 e to the power minus I k r plus e to the power twice I delta L. This is important. E to the power twice I delta L e to the power I k r times PL of cos theta. Okay. You see, the phase of the outgoing wave, the phase of the outgoing wave is shifted delta L, you can say shifted relative to the phase of the corresponding wave by an amount delta L. Delta L is therefore called the phase shift. Okay. So the effect of the scattering potential is to shift the phase of the outgoing partial wave. So we can just add a line here. What is the purpose of the scattering potential? This is the takeaway. The effect of the scattering potential is to shift the phase of each outgoing partial wave. Okay. Now the mathematically the next part is important. Okay. This part is not just so much important. You just need to remember that there is a phase shift in the outgoing wave. Okay. Now the formula which I am going to give you, that is important for your examination. So that is the scattering amplitude. Scattering amplitude. So I just explained the previous one just to make you understand this one. Scattering amplitude is Fk of omega. This is also can be written as Fk of theta. This is sum over L is equals to 0 to infinity. Fk for each L we have to take the sum. Okay. Now this differential scattering cross section d sigma by d omega. This is nothing but the square of this scattering amplitude. And the most important one is sigma, which is integration of d sigma by d omega. This is equals to 4 pi by k square sum over L is equals to 0 to infinity 12 plus 1 sine square delta L. So this is nothing but taking the summation for the scattering cross section for each wave. So this is the most important formula from scattering. What is sigma of L? Sigma of L, this is the contribution of each partial wave, is the contribution to the total scattering cross section, from the Lth partial wave. Now you just remember this sigma of L, this is less equals to 4 pi by k square times 2L plus 1. Why it is? Because sine square delta L, this is less equals to 1, right? Sine square delta L is less equals to 1. So this thing will be less equals to 4 pi by k square into 12 plus 1, simple thing. Here this delta L is known as the phase shift. So mainly question come from this formula. Sigma is equals to 4 pi by k square, somewhere L equals to 0 to infinity 12 plus 1 sin square delta L. Now what kind of problem we get to see? Let us talk about. Like this problem came in December 2017. A phase shift of 30 degree delta L value is given is when a beam particles of energy 0.1 MeV is scattered by a target. When the beam energy is changed, the observed phase shift is 60 degree. Assuming that only S wave scattering is relevant. S wave means L is equals to 0. The cross section does not change with energy, the beam energy is. Can you calculate this? For an energy of 0.1 MeV, we get a phase shift of 30 degree, and when the energy change, we get a phase shift of 60 degree. So if S wave is considered, what will be that energy corresponding to this phase shift of 60 degree? Did you understand the question? So you see, we know the formula of sigma 4 pi by k square sum over L is equals to 0 to infinity 12 plus 1 sin square delta L. This is we know. Only S wave is relevant. So only S wave scattering is relevant, means L is equals to 0. Okay. Now this K is what? K is nothing but square root of twice ME by H cut square, right? And hence the sigma value will be 4 pi by k square. If you take L is equals to 0, it becomes sin square delta 0. L equals to 0, sin square delta L, so sin square delta 0. So this will be equals to, if you put the value of k square twice ME by H cut square, so this becomes 4 pi H cut square divided by twice ME sin square delta 0. Okay. Now you see, cross section does not change with energy, so the cross section will remain same. Cross section for the phase shift of 60 degree is equals to the cross section for the phase shift of 30 degree. So as per the problem, as per the given condition, what we have, let's say 4 pi h cut square by 2m, these are all constant. So sin square delta 0 by E is constant actually. So sin square delta 0 means firstly 30 degree divided by E. E was 0.1 MeV, right? This should be equals to sin square 60 degree divided by energy. We do not know this energy, we need to find out. So energy E is equals to sin square 60 degree by sin square 30 degree times 0.1 MeV. Sin square 60 degree root 3 by 4 or root 3 by 2. And root 3 by 2 and sin square 30 degree. Okay, sin 30 1 by 2 1 by 4. Acha. So root 3 by 2 whole square 3 by 4 and 1 by 4. So it is 3. 3 into 0.1, 0.3 MeV. That's matching with option B. क्लियर दोस्तों? Is this problem understood? Can we move to the next problem? Karthik, is it clear? Where is Murli today? Murli? Do this one. Consider an elastic scattering of particles in L equals to 0 state. If the corresponding phase shift delta naught is 90 degree, the magnitude of the incident vector is square root of 2 pi Fermi inverse, then the total scattering cross section in units of Fermi square each. Look, the particle is in the L equals to 0 state. Corresponding phase shift delta naught is 90 degree. Magnitude of the wave vector means k is square root of 2 pi. So what is the total scattering cross section? Everything is given. We know the total scattering cross section. Total scattering cross section sigma is equals to 4 pi by k square root sum over L is equals to 0 to infinity 12 plus 1 sin square delta L. Now elastic scattering corresponding to L equals to 0. So for L is equals to 0 and incident wave vector is square root of 2 pi Fermi inverse, and delta naught equals to 90 degree, we get sigma is equals to 4 pi by k square means square root of 2 pi whole square. L equals to 0, so 2 into 0 plus 1 sin square delta 0 sin square 90 degree. So this is 1 and this is 1. So 4 pi by 2 pi. So 2. So 2. Here we have used the unit in femtometer. So the unit of sigma will come Fermi or femtometer square because it has the unit of area. So 2 femtometer square. So option A is the correct option. Okay. One last question we will be doing for this session. This came in June 2015. A particle of energy E scatters of a repulsive spherical potential given by V of r is equals to V naught for r less than A and it is 0 for r greater than equals to A. V naught and A are positive constants. In the low energy limit, the total scattering cross section is given by this, where k square is equals to this. In the limit V naught tends to infinity, the ratio of the classical scattering cross section from a radius sphere of radius A each. Ratio of sigma to the classical scattering cross section from a sphere of radius A. Look, this information is classical scattering cross section from a sphere of radius A. It is pi A square. So we have to find out the ratio of sigma and pi A square. This is what we have to find out. Okay. So it is not. It is using the language of scattering, but it is actually mathematics problem. You have been given sigma is equals to this expression. So you have to put the limit v naught tends to infinity, and when in this limit you have to find out sigma, and you just need to take the ratio between sigma and the classical scattering cross section of a sphere of radius a, which we know that it is pi a square. So simply if I put the former problem, so it can be put it in this way. So this potential and all, it doesn't matter. Here we can directly start from the expression given for sigma. Sigma is equals to 4 pi a square times 1 upon Ka tan hyperbolic Ka minus 1 whole square. Okay. Now you see, in the limit of v naught tends to infinity, in the limit of v naught tends to infinity, what will happen? Ka will also tends to infinity. You see, if you put v naught tends to infinity, v naught will decide k square. So k into a will be more than will be tending to infinity as well. So if Ka tends to infinity, tan hyperbolic Ka will be equals to 1. Okay, now how this tan hyperbolic K equals to 1? So let me just show you this calculation here. Tan hyperbolic K. So this is the ratio of sine hyperbolic K and cos hyperbolic K. Sine hyperbolic K is e to the power K minus e to the power minus K divided by 2, and e to the cos hyperbolic K e to the power K plus e to the power minus K by 2. So 2 get cancelled. So we have this one. So if I write e to the power K, then 1 minus e to the power minus 2 Ka divided by e to the power K, if we take common, 1 plus e to the power minus 2 Ka. Now for K tends to infinity, this e to the power K and e to the power K is getting cancelled. So we have 1 minus, okay, e to the power K and e to the power K is cancelling. 1 minus e to the power minus 2 Ka, this is 0, but if you put K tends to infinity. Okay, if you put K tends to infinity, this is 1 by e to the power infinity, so that is 0. Here also 1 by e to the power infinity is equals to 0. So 1 minus 0 1 plus 0, that is 1. So tan hyperbolic equals to 1 for K tends to infinity. So it is better if you write tends to 1, because K tends to infinity, because it is, when it is exactly equal to infinity, then it will be exactly equal to 1. As we are writing it approximately or tending to infinity, we have to write it tending to 1. Okay. So if this is so, sigma becomes 4 pi a square into 1 by Ka, tan hyperbolic K is 1 minus 1 square. This is for K tends to infinity. Okay, now Ka tends to infinity, so 1 by K is 0, right? So this can be approximately written as 4 pi a square, 1 by K is 0 minus 1 whole square. So this is equals to 4 pi a square. And classically what is given? The classical scattering cross section from a sphere of radius a is pi a square. So if I denote that classical scattering by sigma c for classical, so this we go get pi a square, and hence the ratio sigma upon sigma c is equals to 4 pi a square divided by pi a square, that is equals to 4, and this is precisely matching with option A. Clear? I hope you have understood this question. So is there any question you can ask? Otherwise let's end the session here today. On the next class we will be discussing Born approximation. So that is a very important topic to complete. Born approximation. After Born approximation we may go for relativistic quantum mechanics, and after that our quantum mechanics course will be over. Okay, so thank you guys, thank you very much for joining this session. I hope you find this session useful. Bye bye, take care, have a great day.